So with this, we're going to move to our first formal speaker, and that is going to be Bob Langer, who's going to talk to us about enzyme engineering. And Bob, I'll let you introduce the topic specifically and go from there. And if we can get the...
It's not going to work that way.
It's not going to work.
Maybe what we want to do is move to the side projector, and you have a little bit more of an angle. I can roll the podium back out if you'd like to go that way.
Bob, do you want to be able to see your slides while you're talking?
Sure. That wouldn't hurt. Yeah.
We're but as long as they work, I will. Thank you. Thank you, Keith, and thank you, Clark. It's really an honor to be able to present today. So this was my title, and I have to apologize to everyone that I can't stay for very long because it's my granddaughter's second birthday, and I promised to drive to Greenwich, Connecticut to be at her party. Here is my two granddaughters. But again, my apologies for that. And I see many of Clark's grandchildren today, which is wonderful to celebrate all the things he's done. So this is, I Xeroxed a copy of my thesis. You could see Clark's signature. You know, as I'll go over, I had a pretty long thesis. There was only one person I know that had a longer one, which was Clark. But I'll get to that in a minute. Nick Pepis was kind enough to give me pictures. You know, one of the great things for me when I was here in 70 to 74 was making great friends who have stayed with me my whole life. Nick, certainly one of them, and Bob Bratzler I've also done a lot of work with, and Vince Velker. But Nick is really unbelievable when it comes to pictures and so many other things. Here's Clark and Ken Smith. You know, when I look back at those years, there's so much that I learned. You know, maybe some of them you might learn anyhow, but a lot you probably wouldn't. You know, one of the things that was great, and you just saw it in Keith's talk, is exposure to, and I'm going to go over these because it really affected my career, was exposure to big medical ideas. A second, which I'm almost embarrassed to say, was learning how to deal with failure, and because I failed so many times in different experiments. But it teaches you how to persevere in the face of criticism and failure. The third was exposure to companies. And fourth was actually taking a project from start to finish, which is, you know, a lot of people don't. So all those things ended up being very important as I'll go over my own career. But I wanted to make a slide, and I did make a slide just on this, which Clark in so many ways stood out from so many others in terms of these kinds of things. First, he hired, and this was not that common in the 1970s, hiring really great postdocs. I was so fortunate to have Colin Gardner as a postdoc who taught me how to work in the lab. I often tell Colin that was his biggest failure, but it really was incredibly helpful to me to have that. Secondly, we had a tremendous number of Europe students, and that was really terrific, and I think reinforced a lot of my interest in teaching. Third was Clark was unbelievably thorough. Whenever you showed him data, you know, he kept asking about, well, you know, incredibly detailed questions about why, you know, the data or the curves look the way they did. And the fourth, as I mentioned, is along those lines of being thorough, is writing a very long thesis. So mine was 758 pages. Clark's, I think, is about 790 something pages. So And the last point was that he worked incredibly hard. In fact, if you wanted to see him, by far the best time was to go into his office at 2 a.m. in the morning. So these all would come back later on in my own life. So Keith said, well, what we're supposed to do is tell you about, you know, what we did sort of scientifically. So I'll sort of try to do that. So, but maybe just how I got there. So when I got done with my degree, you know, this was 1974, there was this big gas shortage. You know, if you were around then, you'd see you'd have to wait at a gas station for 2 hours to get your tank filled up. The consequence of that, though, is if you were a chemical engineer, you got a lot of job offers. And many of my colleagues went to work for oil companies. So I thought I'd do the same thing. I got 20 job offers, 4 from Exxon alone. And believe me, I wasn't very good for those of you that remember me then. At any rate, I wasn't very excited about that. I was looking for a way, to make some kind of impact, beyond just increasing the yield of certain petrochemicals by a small amount. When I was doing my PhD thesis, I had this extracurricular project. I helped start a school for low-income kids in Cambridge, and I got involved in creating new chemistry curriculum, and I really liked that. One day I saw an ad to be an assistant professor at City College of New York to do just that. So I wrote them a letter applying for a job, but they didn't write me back. But I liked that idea, so I kept finding all the ads I could to do something like that. I found about 40. I wrote to them, and I don't think any of them wrote me back. So I started thinking, what other way could I use my chemical engineering background to help people? I thought about medicine. So I wrote to a lot of hospitals and medical schools, and they didn't write me back either. But one day I was walking into the lab, and one of the people working with Clark was Barry Bunow. And Barry was a very, very bright guy. He said to me, Bob, there's a surgeon named Judah Folkman, and he said sometimes he hires unusual people. And it wasn't really a compliment to either of us. But at any rate, I wrote him, and he was kind enough to offer me a job. I had never heard of him before. Clark had, but what he wanted to do, he had this theory: if you could stop blood vessels, maybe that would be a new way to stop cancer. Turned out that it was a very controversial idea. He's widely criticized for it. I didn't know anything really about biology. I thought it sounded pretty cool. So even though it was by far the lowest paying job, I took the job. And the biggest problem was there was no way to study blood vessels, so we had to invent one. And the problem is there's always background blood vessels wherever you might put things, but there's a couple places where they're not: a chick chorioallantoic membrane and corneas. So our idea is we put certain tumors, which will, as I'll show you, bring blood vessels in. And then we'd want a tiny delivery system, like a micro or nanoparticle, that could deliver large molecules. Now, this is 1974. There was very little work done in this area. One company, Alza, that was the only one really working on it, and Dr. Folk was on their board, and he went and asked them. They would later, by the way, develop all these transdermal delivery systems. But they told him this was not really going to be possible, that to do large molecules, people were just doing small lipophilic molecules. But if we were going to solve the blood vessel problem, we had to solve this problem. So I spent several years working in the lab, experimenting with different designs, different materials, different techniques. I actually found over 200 different ways to get this to not work. But eventually we were able to make these tiny particles. You see a picture of one, and one cut in half. And we showed in the journal Nature that you could use these to deliver large molecules. And my understanding is this is the first paper to show you could use tiny particles to deliver nucleic acids like DNA or RNA. So I was happy that we did this, but the problem is that as we publish papers, being an engineer, I tried to get grants, and my first 9 were rejected. They'd go to like pathology study sections, and they'd say, well, Dr. Langer's a chemical engineer. He knows nothing about biology and even less about oncology, which I thought was mathematically impossible, but it didn't really matter. So anyhow, I didn't get those grants, and then I applied for faculty positions again, but no chemical engineering department in the country would hire me. I mean, because they thought I should be doing energy or mathematical modeling or things like that. And I had these delivery ideas. Eventually, Dr. Folkman, he introduced me to Nevin Scrimshaw. Nevin was head of the nutrition department. And I don't know if any of you remember him, but he was a benevolent dictator kind of department head, which for me was good in a way because he liked me and he hired me as an assistant professor, but he didn't ask anybody else in the nutrition department what they thought. And even that might have been okay, except for one thing, was the year after I joined the department, he left. So a lot of the senior faculty told me I should leave too. And in fact, just to back that up, Mike Marletta, who was there at the time, once gave a speech when I won some award. I'll just read you one line or a couple lines he said. He said, well, one evening I went to a faculty, he was referring to 1979. I went to a faculty dinner at a Chinese restaurant with me and some senior MIT professors. He said a senior scientist sat quizzing us while smoking a cigar. He said, when the older scientists heard my concepts for drug delivery, he blew a cloud of smoke in my face and said, you better start looking for another job. And he said he thought he was in a Fellini movie. So that wasn't so good. But fortunately, I'm still here, and because we had developed the little delivery systems, and I'll just show you this quickly, we showed for the first time that you could stop blood vessels. And these techniques, this was published in Science 50 years ago, really were then used by companies all over the world, mostly starting with Genentech, to actually isolate and purify the first blood vessel inhibitors. It took 28 years from this paper before the first one would get approved. Medicine isn't fast, but starting in 2004, you see one after the next blood vessel inhibitor being approved. Avastin is probably the number 2 or 3 best-selling biotech drug in history, and they're not only used for treating cancer, but different eye diseases in the back of the eye, like macular degeneration and diabetic retinopathy. Also, one of the things we thought about was filing a patent. And so we did. And 5 years in a row, that got rejected too. And I remember the people at the hospital said to me, Bob, you are just wasting so much money. You should quit. But that was one of the things I learned back, failing lots of different experiments early on, as I mentioned. So I tried to think creatively, how could we convince the patent examiner to allow the patent, legally, of course. And science, like I say, really wasn't working. But I wondered, as I mentioned, people didn't think you could do this. So what I did is I searched the literature now in 1982 to see who had written about what we did. And one of the things I found was this quote, and I had no idea this was written. I'll just read it to you. It says, generally, the agent to be released is a relatively small molecule with a molecular weight no larger than a few hundred. One would not expect macromolecules could be released because of their extremely small permeation rates. However, Folkman and myself have reported some surprising results that clearly demonstrate the opposite. So I showed that to the people at the hospital, and they showed it to the examiner, and the examiner said, gee, he had no idea. He will allow the patent if I could get written affidavits from each of these 5 people that they really wrote that. It's a true story, actually. It's a good thing to know if you're filing patents. But at any rate, now with this, it was 10 years later after I'd gotten my degree with Clark, and I was very excited about this. And companies now finally were starting to call me up. And I always had this dream, starting in Clark's lab, that maybe something I do might help people. So these two multi-billion-dollar companies called up, one in animal health, one in human health, asking if I would consult, and they wanted to use the patent. And they actually gave me a pretty good-sized grant. And I was so excited about this. But what happened is that they worked on it for a year or two. I did get a better car. I had a Ford Pinto that was falling apart. But but they both gave up after a year or two. So Alex Klebanoff, one of my friends, said to me, Bob, one day, now we're like in the mid-'80s, we should start our own company. So I kept doing that. I've part of it, again, was exposure to industry. And because of those companies and the people who work there are all kinds of products, that different people have licensed, or companies we started, ranging from new cancer treatments to drug-eluting stents. Actually, Elazar Edelman was one of my students who did a lot of that, just won a Killian Award at MIT 3 days ago. They're not limited to medicine. It's helped enable this giant area of aquaculture in the bottom right. And I thought I would just highlight, to close this, a couple of these things. One of the companies one of the things that's been a big deal is genetic medicine, and people would keep saying how delivery is a big problem. So one of the companies that I helped get started, it was on the founding scientific advisory board, was Alnylam. Kinnikinck, one of my students, actually led the development of Onpattro, the first siRNA drug, which is used to treat a nerve disease, ATTR amyloidosis. That was approved in 2018. But I also got involved in starting a company called Moderna, again, using nanoparticles to protect, in this case, messenger RNA, because if you didn't do that, they'd get destroyed. And that, of course, would lead to this Moderna vaccine. But thinking towards the future, one of the things I hope it will also do is provide new treatments for cancer. And really, it's the same idea as with the COVID vaccine, but rather than attack the spike protein, which is what you want to train your immune system to do, now you go after all the mutations that the tumor has, top 34 mutations. And you can see when you look at the data that 2 years, 3 years, and 5 years, that basically the tumors, you get 50% improvement, even compared to Keytruda, which is the best drug in the world. So this is some of the lessons I learned from Clark. And just one last picture of Clark and me that Nick also gave me. But I don't think I ever would have been, well, I know I never would have gotten all of the things that I've been fortunate enough to have without having had the exposure to Clark and the lab that he ran. And I just want to congratulate him for all he's done and what a magnificent career he's had and influence he's had on all of us. Thanks so much.
I'm Bob Ratzler, class of '74. Bob Langer and I started on the same day, and I think we got our thesis done a similar time, and I never counted the pages in my thesis, okay? But when I go home, I'm going to. I was advised very early on to write a long thesis. And I didn't know Bob Langer had the same advice. And the more you write, I mean, because Clark wants more and more and more. And that was frustrating. So my wife, who typed my thesis, she had a burden. In those days, no computers, no nothing. And if you make a mistake, you got to go back and white it out. Anyway, that's not what I want to talk about. I don't know if I'm one of the 15 or 19 grads that went on to academic positions or not. Because I only...
that was just from Athro.
Just from Athro?
Oh, no, 7 were not. 7 were not.
All right. Well, let me take you through a journey that's rather circular. And I hope to show you how atherosclerosis is connected to migraine. And that's been my career. And you can understand that Clark had a very important part in that, as did MIT. And I'll go through the circle during my talk, okay? So this is MIT. I came in the fall of '74, and there was all these bright students. And I had come from industry, if you want to call Procter & Gamble working on shampoo and toothpaste as industry, from my undergraduate degree at Michigan. And I had to avoid the draft. Some of you aren't old enough to know about this thing called the Vietnam War. And I didn't want to go in the Army, so eventually I got a way to get around that. And here at MIT, I was introduced. I couldn't work with Merrill for the same reason that Clark couldn't, or Clark did. I was introduced to Clark, and I wanted to work at the interface of biology, medicine, and membranes. And I had the perfect project. Figure out how LDL, low-density lipoprotein, accumulates in the interior of the blood vessel wall, look at the transport properties, and I won't go through that, multi-layered laminate structure of the blood vessel. So where does the LDL go? How does it get in? We did all that work. Is convection important, or is it all diffusion, and et cetera? And I was fortunate enough to have 3 great advisors. Now, this is a lesson I learned. You want to work with stars in your career, people that challenge you in both intellectually and work and whatnot. And I can't read the slide, but these are the lessons from Clark. Take risks. I've never done atherosclerosis before.
Can you use the microphone for Zoom? Thank you.
Work hard. 2 a.m. was not my thing. Lifelong learning. If you're taking risks, go, like Bob Langer, go into different fields along the way and have fun. He taught me to be curious, believe it or not. Work with stars in, what's the last one? All right, well, let's move on. All right, so now we're going to go to the circle. The reason I was asking if I was one of the academics or not is I went to Princeton because I wanted to come to MIT and be a professor. My father was a professor. I thought it was a very cushy life. However, in 1976, I think this is, it wasn't a good fit. You have to work at the interface of biology and medicine with somebody who is a star in biology and medicine. And you learn something, and the two combined make beautiful music. That was the theme of my career. Academia didn't quite work. I was interested in membranes. You know, the blood vessel's a membrane, and transfer in a membrane. I couldn't get I didn't want to work in faculty, couldn't get a job. So I went into industry at Polaroid. Now, do you see that diagram? That's the cross-section of a film, an instant film. Think about diffusion, mass transfer, the whole bit. Clark, you didn't work on this one, but it's not medically related, okay? So I didn't, that wasn't a good fit either. So here we are. Let me tell you about Seprecor. So Clark, as Bob, who said this? Job opportunities. Clark introduced me to a gentleman named Tim Barbrick, who was going to start a new company called Seprecor. And Clark said, I could be the vice president of R&D. And I said, well, this is great, because now I'm working with membranes, and we're doing something biologic. So I worked on something called a hollow fiber membrane enzyme bioreactor, and we were using that to separate isomers in drugs. S-ibuprofen, R-ibuprofen are mirror images. S has the activity, R is just coming along for the ride. So we developed this very fancy device and scaled it up. I was responsible not for R&D, it turns out commercial, they got another R&D guy. That really was disappointing. But I got into commercial development and ended up having about 20 trips to Japan, eventually landing a deal with 2 large companies. Now, single isomer drugs, we think of, well, geez, we're developing the single isomer drug. I mean, we got the process. So let's move up the value chain and patent the single isomer drug. So S-ibuprofen, for example, had never been patented. So what's shown there, I think, is albuterol. Albuterol, the single isomer form, has evolved to peak sales of $600 million a year. So this is the impact indirectly of Clark. Now, Seprecor became a drug company. Now, we also had membrane separations work in biologics, affinity membranes. We were doing work in taking virus out of blood with the New York Blood Center. So we had 3 businesses, and we hived off 3 of them, and I took on Seprecor, Seprochem, and Seprochem became Chirex, king of Chiral, okay? And here it is, work with stars. I don't know if people know that K. Barry Sharpless. Barry Sharpless is a chemistry professor here at MIT, and he's a Nobel laureate. And Nick says twice. So he's a double star. And as well, Eric Jacobson from Harvard. The message here is we needed to make single isomer compounds, and if you do it chemically through asymmetric synthesis, that's what the organic chemists liked, okay? They didn't like enzymes. They didn't like membranes. So this was the company. We had this technology, and we said, well, let's get into the manufacturing business. So we found a company in England called Sterling Organics, and we merged together and went public. That became Chirex. And here we had $100 million in sales, thanks to Sterling Organics. And there's a diagram right there that we were making the key intermediate in another pain drug, acetaminophen. That Chirex got bought by Rome Polanc, so I'm out of a job. And I had the good fortune to be approached by a venture capitalist, and they were starting something called Coley Pharmaceutical. And Art Krieg is another star. And I don't have time to go into it, but he is an immunologist, University of Iowa. He came here, we started the company, and he had this idea that you could use short six-member chains of oligonucleotide and turn on the immune system. And once you turn it on, you can go after cancer, allergy, asthma, a whole range of things. I won't explain that slide other than to say immunology is so complex. I'm glad I had a little immunology under Clark, and I used it to at least understand what was going on here so we could develop drugs. So Promune was one of the drugs we developed for late-stage cancer, immune therapy. It got into phase 3 trials, and unfortunately it didn't work. We had some other drugs as shown there. So now I'm really into drug development. And next, Selecta. So Coley was to turn on the immune system. Selecta, there's another immunology slide that I won't take you through, was just the opposite. It was turn off the immune system. And there were some indications that, like refractory gout that we were going after. That wasn't a good fit for reasons that I won't get into. Having done drug development, I was thinking, well, geez, we're now in the stage of everybody using phones. Can we treat migraine or prevent migraine using cognitive behavioral therapy on an app? So this was a challenge. I've never developed an app and a digital therapeutic. We thought we might even take this app through the FDA and get it approved. But selling an app to consumers was a new thing to me. And while it worked, we didn't get it far enough to commercialize it. Apple, by the way, has the exact same app now. So we were ahead of our time. Now, rounding third and heading for home, this is migraine. Again, 2 stars. I won't, Brad Shingleton and Fred Brightman. Fred was a pediatric transplant surgeon in Cincinnati Children's Hospital. So migraine, very, very big problem. I suspect somebody in this room has migraine. We were on a fishing trip with these ophthalmologists, and one of them said, you know, one of my patients took the eye drops for glaucoma, and the migraines went away. And we said, well, that can't be true. And we did a little survey, and we found 10 people that had the same outcome. And we said, well, maybe there's a drug here. So for migraine, we didn't think people were going to take eye drops. It's a little inconvenient. So we said, let's develop a tablet that you can put under your tongue, a sublingual tablet, to do the same thing, which is what we've done. Now, what's this got to do with cardiovascular conditions? We talked about atherosclerosis. Turns out migraine has a big cardiovascular component. Migraine has a vascular vasodilation characteristic, and that's what causes the pain in the head. Now, the glaucoma drug we've now tested, we're repurposing this glaucoma drug, we've now tested and found out it's a vasoconstrictor. And so we also found out that both migraine and atherosclerosis are believed to be caused in part by inflammation of blood vessels. Somebody earlier said that inflammation was involved in atherosclerosis. Well, it is. And here I am back at where I started. So we have now taken this through phase 2 clinical trials, and it works, believe it or not. Eye drops under the tongue work. at least in terms of a signal. And we've patented this. And if anybody wants to develop this and commercialize it, please come forward. So here we are, cardiovascular to cardiovascular. And all I can say is thank you, Clark, for giving me the opportunity to work in this area. And I've thought, you know, he changed my life. And if there's anybody in my life that I have to give a hug to and thank, it's Clark. So thank you very much. Thank you.
Good morning. I'm Jay Schnitzer, another one of Clark's former students. I am not going to use slides, and I'm going to take this opportunity actually to have a one-way conversation with my former PhD supervisor. The rest of you can watch and be part of the observers and the spectators, but this is, and it's unidirectional, which is, as you will hear from the presentations throughout the day, would be very unusual for any of Clark's students to have a unidirectional conversation with him. I'm sure he'll get even later. Keith, I'm also going to do you a big favor and get us back on schedule by being brief. So I don't have a lot to say, but the title of my talk, as you might have read, is A Life in the Hyphen. Tales from a Surgeon Engineer. So hyphen, what do I mean by hyphen? Life in the hyphen, the hyphen. Well, there's a chemical engineering term with nearly the same meaning, the interface. You encouraged that, Clark. In fact, you set the example. And I think as we already have seen, both with the 3 talks already and many more to follow, that many of your students listened to that as well and followed on. You taught us to develop deep, rigorous expertise within a discipline, chemical engineering, but then to break out of the rigid silo and seek the boundaries and the edges and explore adjacent fields. Really important to do. And those are the interfaces between and among the silos that would traditionally exist, or what I would call the hyphens. And you had enormous impact, as we have heard already, and we'll hear more today, on all of us here, and then by extension and multiplied geometrically on all of the students, mentees, advisees, and others that we in turn have coached, mentored, taught over the years and impacted. As you know, and I have learned, life is not linear. We'd like to think of it as such, but it's not. And so it should come as no surprise to you that my professional life in particular has been decidedly zigzag. And that's in many ways inspired by you, and I don't apologize for that. I actually am rather proud that I've had this zigzag trajectory. I don't know if you remember, but it all started with a conversation between you and me, between the two of us in your office back in 1973. Yes, nearly 53 years ago, that is correct. And I remember it very, very well. I had just arrived at MIT as a brand new graduate student and was referred to you as a potential advisor. I had just started coursework. It was in September. I hadn't yet taken the qualifying exams. I hadn't yet chosen a thesis. But I met with you in your office back in Building 12. Many of you may not remember that that was the precursor to this building back in the day. And I informed you that I wanted to work on cancer research. You stated, and I quote, "That was fine." But you recommended, your word, that I start on an existing atherosclerosis project for a number of very good reasons, which you proceeded to enumerate to me in great detail in that conversation. I won't recount all of them here. Now, for the audience, I got to take a moment to do some Clark speak decoding, just in case you aren't aware. So first of all, when Clark ever used the word fine, go back and think again. Start all over. Tear it up. Throw it away. If it was a paper, if it was an idea, if it was the first page of your thesis, forget it. Get rid of it. You never wanted to hear that word from Clark. So I heard it loud and clear. And then Clark saying he recommended something. That's a vice grip on a half Nelson hammerlock. This wasn't a recommendation. This was an instruction that I was to obey. So I was smart enough, I agreed. I didn't have a clue what atherosclerosis was. Not a clue. I'd never heard of it. And 10 short years later, I finally had my PhD. And I think 10 years in chemical engineering on a PhD may still be a record in this department, which I hold. During those 10 years, I was fortunate to cross paths and overlap with several peers from Clark's stable at that time, many of whom are here with us today, and you've heard from one already, Bob Bratzler, Guy Chisholm, Eric Morell, George Trusky, Ron Tompkins, Nick Peppis, Martin Yarmish, and many others, and apologies if I've forgotten somebody. Then came the series of zigzags, nonlinear career decisions, medical school, residency, fellowship, Mass General, Boston Scientific Corporation, DARPA, MITRE, and now most recently, Frederick National Laboratory for Cancer Research. I started at an academic medical center, then moved to a private for-profit industry, then went into government, then went to a not-for-profit think tank, and finally a national laboratory. Not a traditional path. But all were connected, Clark, by the theme of working at the intersection, the interface or the hyphen, of medicine and life sciences with the physical sciences, including engineering and mathematics. I spent the early part of my career, most of it in the early days, at Mass General as an academic pediatric surgeon with kind of a classic quadruple threat portfolio. I was taking care of pediatric surgical patients in the operating room as inpatients and as outpatients. I taught and trained medical students and residents in the operating room, at the bedside, and in the clinic, and I had an NIH-supported R01-funded research program going, looking at developmental biology errors that give rise to the problems that we saw as pediatric surgeons. And I did some administrative and other work, including working for an organization known as ChemE, which some of you may know, and also participating in global medical emergency response. More about that in a minute. After 17 years of doing that, I felt pretty happy and secure in my job. I was doing well. I thought I knew what I was doing, and I even told my chief that he didn't have to worry about me in terms of moving on to something else, that I was going to be there for the rest of my career. Now, for those of you younger career or earlier career people, never, never, never do that. Don't ever say to your boss that you're going to stay with him forever, and he doesn't have to, or she doesn't have to think twice about that. You lose all of your bargaining power. 3 weeks later, I got a call from a colleague, 3 weeks after I said that to him. I got a call from a colleague at Boston Scientific Corporation who persuaded me to come over and work with him. I initially said no, because it was, after all, the dark side. But my colleague was both persistent and persuasive, and I went into industry for a number of years. Had a fabulous experience, learned a lot, a bunch of stuff I didn't know anything about, and hopefully did some things that were impactful as well. 4 years in, I got another call, this time from DARPA. This time I didn't say no on the phone. I was smart enough to at least say, I'm going to come and take a look. And I ended up doing a short, incredible tour, overseeing some amazing program managers and supervising a research portfolio spanning from the life sciences at one end to quantum physics at the other, and everything in between: material science, chemistry, physics, mathematics, you name it. Amazing experience with amazing, amazing program managers who taught me a lot. Bob Langer already mentioned something about Moderna and mRNA technology. That actually came out of the DARPA division that I oversaw. One of my program managers, brilliant scientist named Dan Wattendorf, came up with the idea for using mRNA for vaccines and other applications, and that led to the spin out of a company that we now know as Moderna, which the rest, as they say, is history. Following that, I was, after that short tour, I was looking for what was next, and I ended up at an organization known as MITRE. They found me, which was great. It's a not-for-profit government think tank focusing on science and technology. I spent an amazing 12 years there in a number of roles, and exited there when I finished up my tour just last June. And 4 weeks ago, I decided to take on a new role. So this is interesting because, remember, I wanted to do cancer research 50 some odd years ago. Well, I'm now directing the Frederick National Laboratory for Cancer Research in Frederick, Maryland on an interim basis. So I finally get to do some cancer research. What have I learned? Mentors. You helped teach me the importance of mentors. Choose your chief wisely is the advice I always give young physicians and others when they ask me about advice for next steps in their careers. And of course, choose your spouse carefully. I was fortunate to have a series of extraordinary mentors and chiefs spanning many, many years. And I married my best friend nearly 44 years ago. And two, there are life-changing and life-altering events. In my life, 9/11 stands out. Back to the international medical disaster response. I was part of the National Disaster Medical System emergency medical response to Ground Zero and spent 2 weeks at Ground Zero right after 9/11, initially hoping for survivors. Unfortunately, there were none. It was a mass fatality, not a mass casualty event, but rapidly pivoting to providing urgent medical assistance to the workers on the pile. FDNY, the Fire Department of New York, NYPD, the Police Department, and the Iron Workers. Just three amazing, amazing groups. Needless to say, that experience left an impression. Can talk about that over an adult beverage later. The 25th anniversary of 9/11 is coming up in September, by the way, and I plan to be there for that special day. COVID was another event, and we all remember and impacted everybody in this room in one way or another. I helped lead my own institution's MITRE's response and had the opportunity through that to help lead national efforts. Not going to talk about that in great detail, except to say we put together a coalition of over 1,000 private sector entities, not individuals, organizations, to work together on COVID in an unprecedented manner. And I think we accomplished something. So we've learned some lasting lessons globally from all this, I hope, but I fear maybe not. And now, as I said, I'm just starting the next chapter, which I hope will enable me to help shape the future of cancer research in the United States, finally, after 50 some odd years. So two closing remarks. My own parting thought, contrary to public opinion, and maybe contrary to what many of you see here, but Clark, you'll hopefully resonate with this. Electrons were not placed in the universe primarily to run around on semiconductor chips. No. Rather, they were put here to create chemical bonds. And that function has been, is, and will continue to be far more important for the universe. So, point one. But my literary hero, and that great chemical engineer of former generations, Mark Twain, always gets the last word. Always do the right thing. That will gratify some and astonish the rest. Thank you. Thank you, Clark.
Coming up, we're going to skip the break in order to get back on time, so just be aware of that.
Oh, thank you, Keith and Kathleen, for all you did to make this a wonderful day. And I wanted to talk a little bit about my life as a chemical engineer who moved into biomedical engineering full-time. Actually, I came to MIT with an undergraduate degree in bioengineering, minoring in chemical engineering. And Clark was one of the reasons I really wanted to be here, because he was one of the few people who were actually doing biomedical engineering. And I really liked the quantitative approach, the integration of modeling and experiment that he had done. These are some of the events that were very influential to me during my time there. In early 1980, Clark asked me to write a draft of a book chapter he'd been asked to put together. And that really helped me learn about the field. I mean, it was really a great experience, and see also the contribution Clark's lab had made at that point. And gave me some ideas for my dissertation. And then in 1981, I wanted to do cell culture experiments because I wanted to study how metabolism was influencing LDL transport. And while we did animal experiments here in 1981, we didn't do cell culture. No one in ChemE at the time had done that. So Clark contacted Peter Davies, who was at the Brigham and Women's Hospital, and Peter graciously had me in the lab. Peter was a cell biologist, and he didn't know much about engineering at the time, but he was very open, so it was a great experience. The last two experiences helped me with generating ideas, grant ideas, and that was a lot of fun. I did get the postdoctoral fellowship, but being rather poor at the time, I took a faculty position, first at Tufts, and then in '87, I moved to Duke University in the B&B department. Duke has three great things: a fabulous medical school, across the street from a fabulous biomedical engineering department, and a great basketball team. So it's a good combination. Now, you heard a little bit about Clark's impact on the field of atherosclerosis. And what influenced me the most in my subsequent work was the observations that he had made with Mike Stemmerman and Eric Morel of these localized sites of elevated permeability in normal animals, in this case the rabbit, but others showed it in other animals, that were occurring even without any atherosclerotic stimuli, showing that there's a predisposition of certain sites, and within those regions there are some cells that are predisposed and others that aren't. And that had an influence in some of my early career research. My work could be divided into three broad areas. The first, the central area, really stemmed from the work I did in my PhD, although I moved away from LDL metabolism, but got into a number of studies, eventually creating engineered blood vessels where we could model atherosclerosis. Then in another area, I collaborated with Monty Reichert in our department to use an interferential technique he had worked with to study endothelial adhesion to tissues as well as into implant materials such as stents and grafts. And then I got involved in looking at differentiation of skeletal muscle, both in vitro, first in 2 dimensions, then in 3 dimensions, and looking at modulating that. And now, more recently, been applying that to look at diseases such as rheumatoid arthritis and a rare autoimmune disease, juvenile dermatomyositis. I'll just give you a few vignettes to show how what I did at MIT influenced subsequent work, is shown here. As I mentioned, Clark's lab had identified these hotspots of permeability, and we went ahead and mapped those, and my first grad student, Rich Malinowskis, was trying to find associations with factors that might initiate these hotspots. And he couldn't find anything, but he did come across this interesting observation, which was alluded to earlier, about macrophages right below the endothelium in these hotspots. And so I said, follow that up, and you can see the photograph showing them there, which is very interesting. And so we asked, well, what could cause them to become localized to that region? And we thought the fluid dynamics might play a role. So we made casts from our rabbit vessels, and I collaborated with Clement Kleinstewart at NC State. And he did some fluid dynamic simulations, and we treated the monocytes as just rigid particles that were adhesive, but same size and density as monocytes, and just released them into the flow. And lo and behold, they actually touched down the first time where we saw these elevated sites of permeability. So that was interesting. So there's a fluid dynamic factor that affects the transport of monocytes, the immune cells, in the disease. The fluid dynamics also affect the endothelium, and Abdul and many others had worked on that topic. So we went on and asked another question: is there anything special about the monocytes themselves that might promote them to adhere? They have a specialized receptor that is expressed on them that endothelial cells express a counter receptor to. But at the time, most people treated the leukocytes as rigid particles. And so we wanted to ask that question: is that true? And one way to sort that out was to separate the contact time, which is inversely related to the shear rate, and the shear stress, which is the force per unit area, which you could adjust by adjusting the viscosity. And what we found out was that the contact time dependence was the same whether it was rigid or not, but the force dependence was very different. That is, a rigid particle will move much faster, roll before it adheres firmly as the force increases. But if it's deformable, the deformation increases the contact area, and it creates an increase in number of bonds. So that was very interesting. That really, and others have followed up in the field too. So now we have a couple of mechanisms that could explain the localized accumulation of the monocytes where the disease starts to originate. In the meantime, I had written a textbook on transport and biological systems. I taught a course to our undergraduates in biomedical engineering and was unsatisfied because nothing was available. So I convinced two of my colleagues, and we applied to the Whitaker Foundation at the time, who had a grant mechanism to support these textbooks, and they funded us. And there some major influences on the book were two courses at MIT, Bill Dean's course on general and transport phenomena, and then Clark's course in chemical engineering and medicine. So a number of topics and the mathematics that I presented in the book really derived from those courses on kidney dialysis, oxygen transport in the lung, and then pharmacokinetic models. So that was really a great experience, but it took about 3 times as long to write the book as I thought. So a few years later, we wanted to see if we could actually create atherosclerosis in a tissue-engineered model. We got some funding from NIH, and I had a postdoc who worked on this, Xu Shang. And so we developed these engineered blood vessels and could show we had the endothelium there, we had smooth muscle cells in the media. So what we did was we added some of this modified LDL that was referred to earlier in the perfusion media, and then introduced monocytes. And you can see on the right, we could get them in the vessel wall, they would accumulate, and they took up lipid, as shown by the oil red O staining. And both the modified LDL and another cytokine involved in the disease, TNF-alpha, also could increase monocytes, and together it went up even more. So reinforcing that point of inflammation and atherosclerosis being very important. And then we asked if a drug, a statin, had an effect. Statins lower cholesterol, but they also have beneficial effects on the vessel wall. And it was very selective. The statin reduced the uptake of monocytes with the modified LDL, but not with the cytokine. So that was very interesting and a new observation. Now these were straight vessels, so I collaborated with Cam Leong, who's now at Columbia, and he had a great postdoc, Helen Lee, and she used our technology to create branch vessels. She would make 10 or 12 of these at a time, looked at the branch angle, introduced pulsatile flow, and the important thing is the side region where the flow is transiently recirculating. And we also saw that's where the monocytes adhered, consistent with what you see in vivo. So then with a grad student in my lab, Kevin Shores, we then asked the question, if you promote inflammation through PCSK9, could that also affect adhesion? Now, PCSK9 has a major effect in the liver. It regulates the LDL receptor there and affects plasma levels. So this model is a great model to separate the two effects. So we used CRISPR and elevated the PCSK9, and we could show that when we did that, we got more monocyte adhesion than we could otherwise. So there's a global effect from the flow. There's inflammation induced by modified lipoproteins, and then there's local induced inflammation from some pro-inflammatory factors. Now, lastly, I'll mention another disease I've gotten involved in more recently, a very rare disease. It's actually supported by the Progeria Research Foundation here in Boston. And it's a random mutation to the lamin A gene in the nuclear membrane. And it causes changes in gene expression, a lot of cellular changes that create abnormalities. And these children have stunted growth, look old, a little elfin-like, but old looking. And the worst thing about it is they die of atherosclerosis in their mid-teens to early 20s. So that's how we got involved in that. But the atherosclerosis has some features in common with what you or I might get or may have, in the sense there's calcification, thickening of the vessel, but there's also loss of medial smooth muscle cells. So we work with CanCal at Maryland to replicate this. And then more recently, Kevin Shores, for his PhD, wanted to look at the adventitia because it's the outermost layer of the vessel, and it's also involved in this disease. So he created these 3-layer vessels, and he first showed that if you compare the gene expression to that in the native vessels, aorta and coronary arteries, it's very similar, better than the 2-layer vessel model. We got a better representation of the loss of smooth muscle cells and then very inflammatory conditions. So we've been focusing on atherosclerosis, but from many different angles. So what I learned from Clark, and you've heard a lot of this before, I think one thing I'd stress is independence. I got a lot of independence. I mean, I went off and was able to do my thing and came back, and Clark gave me advice. You heard all the advice that the others gave. He'd write a single word sometimes, and I'd have to rewrite a whole chapter, but it was very great. The discipline and the rigor were very critical. And also, as you see here, chemical engineering really provides a very rich background for someone working in biomedical engineering. So thank you, Clark.
Okay, well, I'm Abdul Barakat, and I wanted to talk a little bit about Clark's impact on my academic career. I actually was probably one of the last students to work on the atherosclerosis project with Clark. But in the title, I also included this bit about tick marks on the inside of axes as a little tongue-in-cheek. Everybody who worked with Clark probably knows what I'm talking about. Tick marks had to go on the inside of all axes, right, Clark? They don't go on the outside. Right? Tick marks, right. Always on the inside. So, okay. So I did my PhD with Clark and finished in '94. I worked on atherosclerosis, and these two images actually came from slides that Clark had introducing atherosclerosis, early atherosclerosis, advanced atherosclerosis. I worked on the hotspots that George talked about and that Eric Morell and Jay Schnitzer and Ron Tompkins and George Trusky and others had worked on. So I was tasked with mapping these on the surface of the aorta and to relating them to the fluid mechanics, right? George alluded to this a bit earlier. So I spent a lot of time studying arterial blood flow in the rabbit aorta, and we ended up generating a lot of detailed maps of flow fields like you see here, right? So, and these, I say, they're ARCO certified, and what I mean by that is Clark worked with a graphical artist at ARCO, right? And we used to go over there, and they basically drew a lot of these plots for us. And you see, these are streamlines, fluid streamlines in the aorta. And there's a lot of information here. Every little tiny detail had to be right, of course, right? So you've got, and you also have different dashing patterns in these streamlines to give you a sense of the three-dimensional structure of the flow field. So solid streamlines are in the plane of the slide. Long dashes are slightly out of plane, and smallest dashes are all the way near the top and bottom walls. And you might imagine with Clark's attention to detail how many iterations we had to go through with ARCO in order to make sure that the long dashes weren't short dashes, and the short dashes weren't long dashes, and the solid lines were truly solid lines. And at one point, Clark told me, "You wouldn't believe this manuscript is costing me $10,000 to draw all this." So we, it was a huge number of iterations that we had to go through with ARCO to construct these maps of the detailed flow fields. During my PhD, Clark actually struck up a collaboration with a group in Paris, the group of Pierre Perronneau, who had developed a technique for doing high-resolution pulse Doppler ultrasound measurements of detailed flow fields. And I got to spend 3 months in Paris doing experiments, and that was extremely productive because I managed to meet the woman who actually became my wife. So Claire and I got married 31 years ago, and we now have a daughter, Maya, who is 21 years old, just turned 21 last month. So this was a wonderful time during my PhD. Thank you, Clark. And what I really appreciated about working with Clark are a number of things, and this has already been said, but I'll say it again. I really felt that Clark, even early on, I felt valued and trusted. And for a young PhD student, that is very important because it gives you confidence and allows you to actually move forward with a lot of self-assurance. George mentioned scientific independence and being able to explore. That's another thing I certainly felt. We could think really independently and explore different things, and that was always encouraged. And then very open and honest communication, often from Clark to us, and I'll give you a very specific example of that a little bit later. After finishing with Clark in '94, I went and did a postdoc with Peter Davies, who at the time was at the University of Chicago. And George mentioned Peter also. So Peter, of course, was working he's one of the pioneers in the field of mechanical or mechanotransduction in cells. So how cells perceive mechanical forces and transduce these forces into biochemical signals. And with Peter, I worked on flow-activated ion channels, specifically as potential flow sensors in endothelial cells. Actually, I got this postdoc position very quickly. I called Peter and I said, I'm graduating with Clark in February of '94, and I'd be interested in doing a postdoc with you. And he said, why don't you come out and visit? I went out and visit, and he offered me the postdoc, and it was really very quick. And I was surprised that it was so quick. I later learned that several years later, when I was talking to Peter, and I said, I'm surprised you hired me so quickly. Well, this is what he actually told me. So I figured anyone who worked with Clark was probably pretty good. So another example of Clark's impact on my life. Then after a year with Peter, I got a faculty position at UC Davis, and I was there for 17 years. And there I continued working on flow-activated ion channels, and then I branched into mechanisms of force transmission from the cell surface to the nucleus. I started working on endovascular devices like stents and how stents perturb flow fields and how we can optimize the shape of endovascular stents in order to minimize the incidence of flow disturbance. I also got involved in a couple of other areas where some colleagues approached me. Some people working in environmental sciences on nanoparticles were interested in health effects. So we looked, for example, at uptake of nanoparticles by endothelial cells. And then there was a really interesting series of projects where we were looking at fetal trophoblast cells during pregnancy. These fetal trophoblast cells actually enter the maternal circulation and migrate against the direction of blood flow on the surface of endothelium in order to colonize the maternal circulation. And there was a question as to why they migrate against flow. This is very unusual, and so we spent some time studying that's the problem and figured out that the interaction between the trophoblast cells and the endothelium was critical in determining the migration of these cells counterflow. Again, in terms of Clark's impact there, so there were a couple of faculty members at Davis who were very familiar with Clark. Peter Strova was a former PhD student with Clark. He was in chemical engineering at UC Davis. And Ron Phillips was a former PhD student with Bill Dean, who had also gotten a faculty position at Davis. And apparently my colleagues at Davis, before hiring me, went and checked with these guys. And again, the Clark link helped a lot in getting the position. So again, another very concrete example of how Clark made an impact on my life. And then, so I said I married a French woman, and in 2010 we actually moved to France because she wanted to move back home. And so I've been at École Polytechnique, which is an engineering school just outside of Paris, since 2010. And there I've been working on a number of topics. One area we've been working on are these engineered blood vessels. George mentioned a little bit of some of the work they've done in this area. Ours have been primarily motivated in trying to understand cellular mechanics under controlled conditions. We've been using these artificial blood vessels or these engineered blood vessels to understand a number of processes. For example, the process of angiogenesis, formation of new blood vessels. So we've figured out ways to try and control the incidence of angiogenesis in these engineered blood vessels. And we've also been working on platelet fabrication using these engineered vessels. How platelets are actually formed in our body is very interesting. That we have these vessels called the sinusoid vessels, and there are these giant cells, the megakaryocytes, that get embedded in the in the extracellular matrix next to these vessels, and they start protruding what are called proplatelets into the lumen of the sinusoid vessels, and under the influence of blood flow, these proplatelets fragment and they become the platelets actually in our bodies. And so we're trying to reproduce that whole process in these engineered blood vessels. And a couple of other things we're working on are we're actually working on the responses of cells to microstructured or non-smooth surfaces. This is because if you actually take a blood vessel and remove the endothelial cells and look at the basement membrane, look at the substrate on which the endothelial cells live, it's not a smooth surface. It's actually a very rough and curvy surface. And so we try to reproduce these in model systems by looking at arrays of microgrooves, and we've discovered some interesting cellular behavior on those systems. And the last thing we're working on is basically developing ways to map spatiotemporal dynamics of cellular mixtures. So, for example, if you have some cancer cells that are interacting with normal cells, and you want to understand how these things interact dynamically and spatially and temporally, right? Well, you could do this using microscopy. The problem is with microscopy, you actually get a lot of photo damage, and you can't do that for very long periods of time. So we've been doing that with electrical impedance spectroscopy. So we make electrical measurements, and the electrical signals generated by normal cells versus cancer cells are different. So you can use the impedance information to distinguish or discriminate between normal cells and cancer cells. And if you have an array of these sensors, you can basically track the spatiotemporal dynamics of cancer cell interactions and competition with normal cells. Just a few random recollections that I have from my time with Clark. I remember he had a little cartoon on his door that said something like this. It said, "If it weren't for the last-minute panic, nothing would ever get done." I don't know if you remember that little cartoon. Yep. Well, that was I would see that every time I'd walk into Clark's office, and we really put that to real application, right? I remember working on an NIH grant with Clark, and we would order legal seafood at midnight or 1 o'clock. It would get delivered, and we'd pull several all-nighters to put together an NIH grant. I mean, that was I think for anybody who's worked with Clark, you know exactly what I'm talking about, right? So that's one random. Another one is Clark had a Mazda Miata, a red Mazda Miata at one point. I remember that. You still have it? Oh, it's a new one. Okay, it's another one.
3 years and now 12 years.
Well, I must have known the first one, I think. And I remember we were going over to Arco one day, with those drawings of all the dashed lines, right? And I said to Clark, "How do you like this car?" And he said, "It's the best car." And I said, "What do you mean by that?" And Clark said, "It's just the best car." Random thoughts, random recollections. That's something that stuck with me. Another random recollection. So I remember my first year working with Clark, I had started looking at atherosclerosis, learning about atherosclerosis. And at the time, people were debating whether atherosclerotic lesions localized in regions of low shear stress versus high shear stress. And I spent some time thinking about this and doing some simulations and some calculations. And I thought I had something interesting. So I actually wrote up a little report and gave it to Clark and asked him to read it. And it took him a little time, but eventually read it. And then I said to Clark, "I really think we should publish this." And Clark said, "I don't want to pollute the literature." Again, and a very concrete example of open and honest communication. He said there was enough pollution out there. I don't want to pollute the literature. Needless to say, we never published that. So, okay. So finally, I'll just finish up. Lessons I learned from Clark that I continue to apply and pass on. Getting the most out of a data set. I think that Clark had the talent, still has the talent for that. Really looking at a data set, getting the most out of every little tiny bit of that. Attention to detail. I think all of us who've worked with him know that. Importance of agonizing over every word in writing. We would spend so much time going over every little line, every paragraph, every word. Open, honest communication. I gave you an example. And of course, tick marks on the inside of axes. Thank you very much, Clark, and congratulations.
Let me see, my slides must be somewhere there. Yes. Congratulations. What else can I say? I will say a few more as we talk. Not only you are a great scientist, not only do I want to show what you did in the field and for the field, especially in the early days, but at the same time, you are a person who likes to help other people. You saved me. I am what I am today because of what you did to me about 54 years ago, 53 years ago. So let me go fast. We are celebrating his legacy, and we are celebrating at the same time his career. And I have decided to do mostly some comments about his career and less about my career, although I will close with some of them. This, you've seen it already, is his PhD. He came from Cornell in 1964. He finished in 1969. This has passed very, very fast. For one thing, look at the cover page. Nobody mentioned the name of Larry Evans, but he appears to have been the last one that was signing there. But anyhow, this was an incredible piece of work. You've heard that it was 798 pages or whatever. Mine was 697, by the way, number 3. But it was just an incredible piece of work for chemical engineers because more than half of it was concentrating on mathematical modeling. And a good part of it was these techniques, the various techniques that he developed. He redeveloped, you can say. Listen, before him, there were not really that many people that have worked carefully in the artificial kidney problem. And that is the important characteristic of Clark. He is always careful about what he does. Nothing is going to go out without having been checked 10 times, as many other people said. You know what happened to his PhD? A few years later, in that is about 1977, it became a book of NIH on evaluation of hemodialysis and dialysis membranes. And if you look at the last section, it's all the mathematical modeling. about clearance and dialysis and so on, and all the terms. I don't know if the medical doctors understood what he was writing, but it came out. And I still have it in my office, and I still admire it. I did my PhD with Ed Merrill. So I'm an academic brother of Clark Colton. And when I finished in 1973, I returned back to Greece to do the military service. I finished with the military service, and I came back in 1975 around May 20th. I remember it because it was close to the Indianapolis 500 in that year, and I couldn't find a job, nothing. And I went to him about a week before returning back to Greece for the rest of my life. If he had not done what he did, I would be now a very old man without hair, smoking 50 cigarettes a day, and complaining about everything. So anyhow, I went to him and I said, I'm looking for a postdoc, something. And he pulls out his drawer. He looks at something, he closes it, and he says, you're hired. What? And Ken Smith will be with you, and he will be in arteriosclerosis, and Bob Lees, and you will be in the arteriosclerosis center, and so on. It took me about 5 years later when I asked him, what did you do that day that you pulled out the drawer? Oh, I had done the qualifying examinations of January 1972, and I looked to see where you were ranked. And that year was a terrible year. There were 12 of us taking the exams, and only 2 of us passed. Mike Sefton, who sends you his regards, and I. And he said, we had given exactly the same exam in 1963. And there were about 8 people that had passed. So you're really an inferior class. But anyhow, I started working with him, and you can see very nicely. Please look at the left picture with a cigarette, not in the laboratory, actually in the office, over in the arteriosclerosis office, a lot of scintillation counters and so on. And there was a lot of work, of course, with Jay Snitzer and a few other names that I'm going to mention. I followed the work of Bob Bratzler and Guy Chisholm, who unfortunately is not with us today because he had a rather significant operation and he cannot fly. But I want to show you 2 things because it's very important for me that you, and especially the young generation of chemical engineers who are not here, understand what Clark did not only for MIT, but for the field. Working with Clark in the 70s and 80s, I mean, he loved this place. He wanted to see it #1 in the country. Why? Because in 1977, there was a ranking of ChemE departments by somebody called Bill Gill. And this Gill ranking had us as #7. And that was terrible. MIT #7. So he took over the graduate exams. And of course, he was 1 year, he was chair of the department until Jimmy Way came. And then, of course, Bob Brown and so on. But during that time, he was doing great things. Of course, I can say this paper was written by Bob Langer and me. But there are some important things up there. I don't know if you can see it. That Clark Colton and Ed Merrill of MIT, and of course Lightfoot and Alan Michaels were the early ones who were doing applications of chemical engineering to the biomedical field. Of course, we recognized him at that time predominantly for biomembranes, basically for his work on artificial kidney, but there are many other areas, very, very, very early. And the other thing I want to show you, this is directly out of his PhD thesis, that I mean, you look at this nice diffusion cell and you say, it's not really anything important. It is, and he has spent a lot of time doing it. And many of us did it again in order to analyze the transport through systems. So for me, biological transport was something that Clark Colton developed from a more fundamental point of view. Because as you know, I'm a little bit more fundamental and less translational. And you can see various comments that were made about how he was the leader in the field as some of his very early papers. I did an AI analysis, and I asked an AI, what is Clark Colton known for? And I want you to see, look at the scientific contribution. His work led to the foundations of modern biomedical engineering approaches to understanding vascular disease. With all due respect to my young BME colleagues, If you ask them right now who developed and who did the foundation of that, they will not know. Because unfortunately, the field changes so much, and everybody's crazy about their new developments and their new companies, and they don't understand that it is material subjects like these that have really changed the field. This is a very nice paper that I wanted to show for a moment. This is from Bob Ratzler. Correct, Bob? Did you draw that? I think probably you did. Or it was Yarko, yes. But it was great because it shows you really how we started analyzing now the structure of the arterial wall in various levels. And we would go painstakingly, and we would have the transport of LDL containing, of course, the cholesterol or whatever, passing through the cells and also coming from the other side, from the interstitial side, and trying to see this transport using what? Iodine 125. So all the experiments were appropriately radioactive, and that's very important because the last day at MIT, before I went to Purdue, I had an accident with iodine 125. And they had, of course, to get rid of all my clothes, and I had to be counted continuously for 58 days. But it was a magnificent way of analyzing. Of course, we would do cryotomy. Oh my God, Jay, do you remember the cryotomy? It would take a long time and so on, but we were able to come up with these incredible concentration profiles. Which I will show you in a minute. In 1977, Clark was the wunderkid, if you wish, of chemical engineering. In 1977, he got the Alan Colburn Award, which is a major award in chemical engineering. He had gotten a lot of other awards. This is from that time. And so on, he was happy. He would come to the American Institute of Chemical Engineers meeting, where there was something called the Exxon Suite. We would arrive on Sunday afternoon, we would say, where's the Exxon Suite this year? And they would give us a number, and we would go there. And he would he would be there, 7 o'clock in the evening until 2 o'clock in the morning. And he was always so happy. I mean, this face that you see there, always very happy. And it was there that we discussed how Bill Gill had charged and put us number 7, and we're going to change that. And he was talking and talking and talking with Gary Leal, with Henry Weinberg, with some of the people of that time. I learned from him so much you cannot imagine. He made me competitive. Ed Merrill was a great man, my major professor, but he was not competitive. He was competitive, and I love it. I love that. And a few pictures, of which the fourth one, you saw 2 of them, you didn't see the other 2. The fourth one is the one that I want to spend a moment for. This was the old building. I think it still exists. And that's where Clark started. And you see this little thing on the very top there? That's where some of his students were. That's where Jerry Meldon and Bob Ratzler, I think, and Bing Van Dyke, and Langer, even Langer up there, and Wayne Pitcher, and so on. They were up there, and you had to go with some stairways all the way to the top, and they were isolated there, and they were doing great work. I remember that building very, very well. And now I have 2 pictures that will bring back a lot of memories, and they are from the Arteriosclerosis Center. And one picture is here showing some of the Langer people and other people in this particular gathering. And the one in the middle, her name is Bernie Cusack. She was in charge of the laboratory. To her right is Carlos Ramirez, one of his PhD students that was not mentioned today, who went to the University of Puerto Rico in Mayagüez and retired. Next to him is Larry Feig. Maybe you saw him last night. Master's degree, and then myself here at the very right. And there were so many others. Of course, I have Jay Snitzer in there, and Guy Chisholm, who was the postdoctoral mentor. I'm sorry he's not here with us, Bob Ratzler, and so on. And I wanted to mention also somebody who is on the left of that picture, and that is Alan Golombitsky, one of the undergraduate chemical engineers who went on and became professor of medicine at the University of Texas at Houston. So you can see his impact has been incredible. And this is the picture with which, if I listen to Katie, I should stop. But this is the picture that shows, do you see the one on the very left corner up there? That's me. And under that is Larry Feig. And please look at this young lady next to Larry Feig. That's Rena Bizios. Rena Bizios in the back, and she knows that picture. And of course, Jay Snitzer is to her left, and Guy Chisholm is a little bit further back. These were all Colton people that were in the laboratory. And these were the things we were doing. Look at this study. This is a magnificent study that shows accurately what happens in the aortic wall during the transport of LDLs. At which point, I want to say two things. One is to the Colton grandchildren, and to anybody else that is of their age, do whatever you want. You have an idea, discuss it with a senior in the family, with a grandfather, with the others, and try to do it. Don't listen to others and say, oh, no, that's difficult. Oh, no, you cannot do that. Oh, you like dancing, and so on. Don't do dancing. Of course, Helen always, it was very much in theater and dancing and so on. So do whatever you want. And the second comment that I wanted to make is what he has done has affected all my work in the last 50 years, all the drug and protein delivery, and through him has affected also the next generation after that. My wife, Lisa Brown-Peppers, would not be what she is now if it were not for the work he taught me and which passed to her, and which led to her many companies and eventually the membership to the National Academy of Engineering last year. So two people are telling me to finish. I wanted to show this. This is something that was not shown. This was a partial academic family tree, which we did for him about 20 years ago for the ASCHE meeting. And it has all the names. And this is him giving a talk in this room about 15 years ago for Ed Merrill. And you please look at this picture. You see how happy everybody is. He was magnificent that day. And he told everybody all the great stories about living on the third floor. So thank you for everything you've done. I'm glad I didn't start crying. And many, many years, as the Chinese said, 1,000 years to go. Thank you.